Welcome to Chapter 4, Utility. In Chapter 3, which dealt with preferences, preferences represented consumer choices over a set of bundles. What we did is we looked at these pictures of indifference curves that showed the rates at which consumers were willing to trade one good for another good, to move along bundles. Indifference curves defined a set of bundles that the consumer liked equally well. Utility, if we wanted to describe it in the most simple way possible, utility is assigning a mathematical label to each one of these indifference curves. We assume that higher indifference curves are better, right? So better indifference curves must have larger numeric labels. It actually doesn't matter how much larger, it's just that better bundles have to have bigger or larger labels attached to them. And that's basically all preferences are. This idea of utility originated with Jeremy Bentham, who was an economist who was active in the late 18th and early 19th century. And Jeremy Bentham was a professor at the University College of London. If you take a history of thought course, you will learn about Jeremy Bentham as the founder of the school of thought known as utilitarians. And the utilitarians believed that society should be organized in such a way to provide the greatest good for the greatest number of persons. And in Bentham's writing, he speculated or he used as a fanciful illustration this idea of a machine that he called the utilometer, that you would hook a consumer up to them and you could measure how well off this person was. So if this utilometer could measure how well off a person is, our modern construction of utility is meant to do the same thing. It's a measurement, it's a mathematical measurement or specification of how well off a consumer is. Now, one of the interesting stories about Jeremy Bentham that I would be remiss if I didn't tell you, this thing that you see on the left is in fact Jeremy Bentham. So Jeremy Bentham was very wealthy and he never married, he had no heirs to his estate. So Bentham's will specified that he would give his entire estate to the University College of London if upon his death he were mummified and placed upon permanent display in the economics department, and would continue to preside over the University College of London faculty senate. So it was a very large estate, and in fact, when Bentham passed away, he was mummified, and to this day, almost 190 years later, Bentham is still on display at the University College of London. Now, I'm not a Bentham scholar, but Bentham scholars speculate, why was it that Bentham did this? Was it out of ego, or I guess I kind of prefer, for personal reasons, the second explanation. Bentham did this basically to make fun of his colleagues, right? This shows the depth to which university administrators will go to get money from donors, right? So to get Bentham's estate, they actually mummified him and put him on display. For those of you who are familiar with Professor Cunningham, my colleague Scott Cunningham, for a long time his Facebook profile picture, he has a picture of himself next to Bentham at UCL. So Bentham is a larger celebrity now in death than perhaps he was in life. Well, anyway, if we wanted to get away from words, right? Remember, I was trying to talk up Varian's textbook. One of the virtues of it is that he doesn't use many words. So if we wanted to describe mathematically what utility is, we could do it very tersely with this single line. right? So if I say that bundle x1, x2 is strictly preferred to y1, y2, that is equivalent to saying the utility of x1, x2 is greater than the utility of y1, y2. Notice that the arrow points both directions. So the preferences statement on the left implies the utility statement on the right, and the utility statement on the right implies the preference statement on the left. Now, the very first slide of this lecture, I said that it really didn't matter whether we assign what these labels are, right? We stated that better bundles or better indifference curves should have a larger label, larger numeric label, but it didn't matter how much larger. The way we could describe that mathematically is to state that we could apply any monotonic or order-preserving mathematical function to this underlying utility relationship, and that's just as good. So the way we will define a monotonic transformation is one which preserves order, or again, a mathematical definition would be I could differentiate g of u with respect to u, and that derivative is strictly positive. Then we have a monotonic transformation. I'll illustrate lots of examples here in just a bit. So here's examples of monotonic functions, and I've repeated from the previous slide the definition, the mathematical definition of a monotonic transformation. Multiplying by 6 and subtracting 2,500 preserves order. So for instance, what if I had an initial indifference curve with a utility of 0, and the next higher, better indifference curve had an underlying utility of 1, right? So I apply the first transformation to it. 6 times 0 minus 2,500 would be negative 2,500. The second indifference curve, the second better indifference curve, with the utility level of 1 would be 6 times 1 minus 2,500. So this second better indifference curve would have a utility level of minus 2,494. Right? Negative 2,494 is larger than negative 2,500. So we've preserved order. So this first mathematical function would be a fine example of a monotonic transformation. Multiplying by the constant pi, 3.14, is a monotonic transformation, right? And if we wanted to apply the math to it, if I took the derivative of pi u with respect to u, the derivative is pi, and pi is strictly positive. The derivative of u squared with respect to u would be equal to 2u, and that is positive for u positive. Taking the square root also works. And this final one at the bottom is kind of a cosmic example, minus e to the negative u. And actually, I worked all these out. I shouldn't have to talk you through them. The last one, perhaps we should be a little more careful about. And so if I take the derivative of minus e to the negative u with respect to u, that is equal to, remember, if you take the derivative of e to the anything with respect to that variable, it is the same thing. So we get minus e to the, or we get e to the negative u, and or negative e to the negative u, and then we take the derivative, we apply the function rule, so we take the derivative of negative u with respect to u, that is negative 1, and we end up with e to the negative u, which is strictly positive. So that last transformation, goofy as it looks, is still a monotonic transformation. I believe you have a homework problem that asks you to work through some of these. Okay? Ordinal versus cardinal utility. Now, this example that I talked about at the very beginning of the lecture, that we assign higher or we assign larger labels to better indifference curves, but it doesn't matter how much larger they are. This would be an example of ordinal utility, which says that better bundles get larger labels, but it doesn't matter how much larger. The difference in these magnitudes has no underlying meaning. Cardinal utility would be an example of a utility scheme in which the magnitude does matter. So for instance, if the utility of x1, x2 was twice as large as the utility of y1, y2, then under cardinal utility, the bundle x1, x2 is twice as good as the bundle y1, y2. That would be a cardinal utility scheme. Varian points out that cardinal utility is not widely used. The modern usage of utility is almost universally ordinal utility, which says magnitudes don't matter. Now, the way we will define utility functions is basically, you remember in the last chapter, I made the argument that the shapes of indifference curves carried a lot of very important economic meaning. So it's these underlying relationships that really matter. The mathematics of it is really immaterial, if we want to be really blunt about it. What is important at this point is we need to identify mathematical functions that have level sets which match the shapes of the indifference curves that we're interested in. Now, if utility is ordinal, meaning the magnitudes don't matter, the exact mathematical function we use also does not matter. So if we have a wide variety of mathematical functions that we could choose from, I would argue we should choose the one which is most convenient or simple to work with. So we should take the most simple, convenient function that generates the shape that we're interested in. And that's all we really have to do. So as a first example of it, think again of my lame preferences between Coke and Pepsi, where I think that they're a perfect substitute one for one. I claim that a perfectly good utility function that would describe my preferences is if you just added the number of 2-liter bottles that I have of Coke and Pepsi, right? So x1 plus x2 would adequately represent my preferences. So utility equals x1 plus x2 would, that function, if we want to be more highbrow for a moment, that function has level sets like the diagram that we have on the left, right? So lines with the slope of -1. Monotonic transformations of this, if I could multiply by 2, right? So utility is now 2x1 plus 2x2. I could multiply by 2,000. It doesn't matter. These are all perfectly good utility functions that represent my preferences. If we want to think of our dear friend Shirley Sixpack and her preferences between 8-ounce cans and 16-ounce cans, the important question of the moment is which of these two utility functions that I've shown here adequately represents or accurately represents Shirley Sixpack. Is it utility function 1, candidate 1, 2x8 plus x16, or is it function 2, x8 plus 2, x16? Now I claim a simple way of doing it is we could think of two bundles that we know are on the same indifference curve. So 4 8-ounce cans and no 16-ounce cans. are on the same indifference curve as no 8-ounce cans and two 16-ounce cans. Both are examples of combinations that give Shirley 32 ounces to drink. So the correct utility function will assign the same utility level to those two bundles. So you'll notice from the little table that I have to my left that candidate 2, x8 plus 2x16, assigns the utility level of 4 to both bundles. So that is the correct one. An alternate way of thinking about this is that with the function x8 plus 2x16, what we are saying is that one 16-ounce can makes Shirley's six-pack twice as happy as one 8-ounce can. And that is indeed true, right? That accurately describes Shirley's six-pack. So that's good. Okay, so a monotonic transformation of function u2 might be 8x16 plus 16x16. So that would be multiplying the function u2 by 8. So multiplying by 8 is an acceptable monotonic transformation. Perfect complements could be represented by the minima function. So you remember the minima function states the values that follow in the parentheses. You take the smaller one. So with the values x1 and x2, we pick the smaller one, and that's the utility level. And multiplying by any constant would be an acceptable monotonic transformation. For imperfect substitutes, you might remember from the previous chapter there were two classes of imperfect substitutes that we talked about. One required positive amounts of both goods to get utility. So in this picture that I have on the left, you'll notice that the indifference curve asymptotically approaches both the horizontal and the vertical axis, but doesn't touch them. And what that implies then is that non-zero amounts of both goods are required. One mathematically simple way of doing this is by multiplying x1 and x2. And this is an example of what is known by economists as Cobb-Douglas utility. So I think Cobb and Douglas proposed this functional form for planning purposes back in the 50s. Anyway, it has a long history, but it's mathematically simple, multiplying the variables together. Now, it turns out we could do something a little more complicated. So we're gonna go scholarly. We're gonna use Greek letters. So we could multiply by some constant out front. That's the gamma, right? That's the curly looking thing. And we could also place exponents on x1 and x2. So we have gamma times x1 to the alpha power times x2 to the beta. This would be a more general expression of the Cobb-Douglas functional format. Now, we could take a logarithm of this, a logarithm of x2, of utility function 2, and the question is taking a logarithm, is that a monotonic transformation? To address this in an indirect manner, I remember a story I have to tell you. When I was a freshman, I was crazy enough to sign up for 8 a.m. calculus. And so 8 a.m. calculus 1, my first semester, we had a very fine professor, but he was, I guess this is really terrible of me to say this, isn't it? He was a lot like Hal. He was very organized, very systematic, but kind of monotone and not particularly interesting. But one day in the middle of the quarter, Professor Prather came alive when we were talking about E, which is 2.718. It's the base of the natural log function. So Professor Prather came alive when we considered E. He talked about all the wonderful things that you can do with E, continuously compounded interest and all sorts of things. And he talked about how he had a personal fascination with E and asked how many of us did. And you can imagine with the room of 18-year-olds, none of us moved, right? We didn't want to get mocked by our classmates. And then Professor Prather told the one joke he told the entire semester. So you remember the biblical account of Noah and the ark in Genesis chapter 8 and 9. So in Genesis chapter 9, the ark comes to a rest after the floodwaters recede from the earth. And you remember when the ark came to a rest, God instructed Noah to open the door and dismiss the animals, and God's command to the animals was to be fruitful and multiply. Well, one of the creatures on the ark were this snake from North Africa called the adder. And the adders said, "Lord, we're adders. We can't multiply." And the Lord said, "But my command to you is be fruitful and multiply." And the adders said, "Lord God, we want to obey you, but we simply can't. We're adders. We can't multiply." So God commanded Noah to construct a table out of logs and place the adders on it, because everyone knows adders can multiply on log tables. I can hear you groaning through the internet. And in fact, you can imagine, we all groaned. We thought this was the most horrible joke. But the purpose of it was we remembered how to take the logarithm of an expression. Because you remember, if you have a multiplicative function, the log of a multiplicative function is the sum of the logs. So when I take the log here of gamma x1 to the alpha, x2 to the beta, it is, so I add the logs of the multiplicative terms, and things which are exponentiated in the original function become products in logs. So we have log gamma plus alpha log x1 plus beta log x2. Now, taking the natural log is indeed a monotonic transformation, because the derivative of log u with respect to u is 1 over u, which is positive for u positive. The reason why you might want to take logs is because in log form, this expression is multiplicative versus exponentiated. And it will mean that it's much easier to differentiate additive terms than, it's much easier to differentiate multiplicative terms rather than exponentiated. So despite maybe how it initially appears, taking logarithms actually dramatically simplifies the math. Okay. So imperfect substitutes, so Cobb-Douglas, remember, required that you have non-zero amounts of both goods. And I probably should have emphasized that a little more. Notice that in the function u1, where I have x1 times x2, if either x1 or x2 is 0, it doesn't matter how much of the other good you have. You will have no utility, right? So this mathematically ensures that non-zero amounts of both goods are consumed. For quasilinear utility, it's a mathematical specification that does allow zero amounts of one or both goods. Now, quasilinear, if we want to play English major games for a moment, quasilinear describes functions which are linear in one commodity and nonlinear in the other. So the general explanation of it, which that first math line in the center, nu of x1, that means we have some nonlinear function of x1, but x2 is linear. So utility is nonlinear in x1 and linear in x2. So depending upon which nonlinear function we have, we can get either the behavior that we have on the left or the right. So on the left, what I'm specifying is that I am willing to have, zero amounts of gut packs, but I require non-zero amounts of Dr. Pepper. That would be described by a function, or one example of a function that would generate that behavior would be the log of x1 plus x2. What happens when you take the log of 0? The log of 0 is undefined. So as x1 approaches 0, the log of x1 approaches negative infinity. So this ensures that there is a non-zero quantity of x1. If either x1 or x2 could equal 0, one clever function that allows that is on the right. So we have a function here, 4 root x1 plus x2. We're nonlinear in x1, we're linear in x2, but you'll notice that I would be willing to accept 0 Dr. Peppers if I had enough gut packs. I would be willing to accept no gut packs if I had enough Dr. Pepper. Now, before we go on to the marginal rate of substitution, which remember was the slope of the indifference curve, I wanted to have a very brief review of derivatives. Intuitively, a derivative is a rate of change. So if we had a mathematical function, you remember from your calculus class that if I drew a tangent line, so a line that was tangent to this function f at the point of interest, the slope of that line would be the rate at which the function is changing. So alternatively, we could say it's the rate at which f of x changes as x is increased by a very small amount. For a polynomial, meaning we have a times x to the b power, if I take the derivative of ax to the b with respect to x, you remember from your calculus class that I take the exponent on x, which is b, put it out front, and then I subtract 1 from the exponent. So the derivative of ax to the b with respect to x is ba multiplied by x to the power b minus 1. Okay. In this class, we are going to consider partial derivatives. Partial derivatives are a topic that's usually reserved for Calculus 3, but we're going to do it, and they're not terribly difficult. The way to think about it, a partial derivative is this is differentiating a function of more than one variable. So utility, as we've defined it in this chapter, has two variables, x1 and x2. The partial derivative with respect to x1 is the rate at which utility changes as x1 is increased by a very small amount, holding x2 constant. So the story is, if we take the partial derivative of utility with respect to x1, we treat x2 as if it were a numeric constant, like 50 or 100. And you remember, of course, the derivative of a constant with respect to a variable is 0, right? Because constants are unchanging. So as an example, if I take the partial derivative of x8 plus 2x16, that was Shirley's six-packs utility, with respect to x8, the derivative of a sum, you recall, is the sum of the derivatives. So I could take the partial of x8 with respect to x8, which is 1, plus the partial of 2x16 with respect to x8, which is 0. So what this says is, if I give Shirley six-pack another 8-ounce can, it causes her utility to increase by 1. That's obvious, right? If I ask how 2x16 changes as I change x8, holding x16 constant, so if I treat x16 as constant and I'm changing the number of 8-ounce cans she has, holding 16-ounce cans constant, there is no change in the quantity of 16-ounce cans she has. So that second partial derivative is 0, and what we end up with then is Shirley's utility rises by 1 when we give her another 8-ounce can. Alternatively, if we give Shirley another 16-ounce can, the partial of x8 plus 2x16 with respect to x16 is 2, for exactly the same reasoning process. Suppose that lunch at VTEX, my utility was x1 times x2 squared. So remember, x1 was cans of Dr. Pepper, x2 was gut packs. So we square the number of gut packs. Okay? So if I took the partial derivative of x1, x2 squared with respect to x1, that derivative, remember, so when I take the partial derivative, I'm treating x2 as if it were a numeric constant. So that derivative is going to be x2 squared. It would be like, think of taking the derivative of 50x1 with respect to x1. That derivative would be 50, right? By much the same reasoning, the derivative of x1, x2 squared, the partial of x1, x2 squared with respect to x1 is x2 squared. And then to complete this, the partial of x1, x2 squared with respect to x2, remember, we're holding x1 constant, we're treating it as if it were a numeric constant. This partial derivative is 2x1 times x2. So we take the exponent on x2, move it out front, decrement that exponent by 1, and x2 is treated as a numeric constant. Okay. Now, the marginal rate of substitution, you remember, was the slope of the indifference curve. The slope of an indifference curve is given by this wonderful theorem, right? The derivative of x2 with respect to x1, which is the slope of an indifference curve, is the ratio of these marginal utilities, the ratio of these partial derivatives. This is actually one of the most important formulas that we'll cover in the first half of the course. I am adamantly dead set against memorization. This is a course where if you attempt to memorize things, by the time we get farther into the course, there will be so many things to memorize, it won't be possible. However, I will make an exception for this one result. This one is actually so important. This is one that's worth putting to memory. Okay. Now, this result can be derived using total differentiation of the utility function. So for the sake of completeness, I am going to derive it and show you where this function came from. Moses didn't descend from the mountain with this result. It's easily derived. Okay. So the technique of total differentiation says that any change in the utility level has to come from either changing x1 or x2, right? Because utility is a function of x1 and x2. The only ways of changing the level of utility is by changing x1 or x2. So if I change the number of units of x1 that are consumed, I can multiply those changes in the units of x1 by the rate at which utility changes as I change x1, right? So let's say that the consumer gets 5 more units of x1, and for each unit of x1 that each additional unit of x1, utility rises by 10, right? So we have 5 units change times a rate of 10 for each unit change, we'd get a change of 50. So, and by the same thinking, we have the partial of utility with respect to x2 times units change in commodity 2. Now, we want to consider movement along a given indifference curve. So what that means, we could define mathematically movement along a given indifference curve by saying the change in utility is 0. So what this does for us now is it says if I increase the amount of x1 that I consume, I have to take away some x2 to keep utility level constant, to move along the indifference curve. So I could set that expression at the top of the slide to 0. And then I can rearrange this expression now that describes offsetting increases and decreases in x1 and x2 to remain on the same indifference curve. I can rearrange this to solve for the slope, which would be dx2, or the total derivative of x2 with respect to x1. So I move. So I basically just start manipulating, right? So I move the partial of utility with respect to x1 times x units change in x1 to the other side of the equality. Now I divide both sides by the partial of utility with respect to x2, and units change in x1, and I get my desired expression. This is the expression that we had from the previous slide for the slope of the indifference curve. Now this is a truly cosmic result. So if you want to impress your math major friends, you could say that the slope of the indifference curve, which is the marginal rate of substitution, is robust with respect to monotonic transformations. This has a very intuitive proof. If utility levels, like we said in the first slide, are just a numeric label attached to indifference curves, then if I assign a different set of labels to the curves, changing the label values isn't going to change the underlying slope of the curve. That's rather obvious, right? But we could use the bulldozer to dig up the teacup, right? And we could apply a mathematical proof. So if I apply my favorite implicit function theorem to this new transformed utility function g of u, I could say that the slope of the indifference curve with these transformed utilities is given by the expression on the right. But then when I start to manipulate and simplify this expression, I can apply the function rule. So the partial of g of u of x1, x2 with respect to x1 is the partial of g with respect to u times the partial of u with respect to x1. And then I apply the same technique to the denominator. And you'll notice that I have now this expression the partial of g with respect to u in both the numerator and the denominator. I can cancel that out, and I'm left with my original expression from the previous slide for the slope of the indifference curve, or the marginal rate of substitution. So for this reason, we would say then that the marginal rate of substitution is robust with respect to monotonic transformations. It doesn't matter what label you apply, the underlying slope remains the same. Okay. Now, Varian's text gives precious few examples, but the ones that he uses are very, very good. So this first one that he had was an example of this work done by these two economists, Domenech and McFadden, in the 1960s. So they were hired as consultants to estimate consumers' willingness to pay for tickets for what was then a proposed project in San Francisco to construct the Bay Area Rapid Transit System, or the subway system. I might add that McFadden later won a Nobel Prize in economics, so he's a fabulous economist. So Domenech and McFadden basically prior to BART, commuters in San Francisco either drove to work or they took the bus. And so Domenech and McFadden gathered data set, from surveys from a number of consumers on how they commuted and what it cost them. Did they drive or did they ride the bus? And of course, if consumers are rational, they would pick bus riding or driving, whichever commuting methodology made them better off, they'd choose that, right? So if consumers can be relied upon to maximize their utility, they then used econometrics to estimate these three parameters, beta 1, beta 2, and beta 3. So they assumed that the consumer's utility was a function of how much time they spent walking, the total time that they spent commuting, and the total cost of commuting. And if a subway system were constructed, that would dramatically reduce the amount of time that Bay Area commuters would spend going to and from work. The question was, based on the choices that they made regarding driving versus taking the bus, how much were they willing to pay to reduce their total commuting time? The way that we could do that is by using the nice theorem from the last couple slides. We're interested in the derivative of total cost with respect to total time. That says how much additional cost are consumers willing to pay to reduce their total time spent commuting by an hour. Now, you remember from the very previous slide that this rate at which they're willing to trade cost, which is a bad, right, for total time commuting, which also is a bad, it is robust with respect to what functional form we impose upon the utility. Right? That was the cosmic result from the last slide. What they found out was that the willingness to pay was $1.10. So in 1967, San Francisco commuters were willing to pay $1.10 to reduce their commuting time for 1 hour, whereas at this time the average wage was $2.85. So about 40% of the wage that they were earning, they were willing to spend to recover an hour of their day. So that's basically this chapter in action. Okay, so on to the questions. We will see a whole bunch of questions with Charlie. So Charlie consumes apples and bananas, and Charlie is Cobb-Douglas. Right? So he has a Cobb-Douglas utility function. If Charlie is consuming 10 apples and 30 bananas, what is the slope of his indifference curve? So this is an example of the theorem that we worked out a couple slides back, and the same one that Domenech and McFadden used in the previous slide. I would always recommend, when approaching problems like this, to draw a picture. Drawing pictures will focus the problem for you. It will give you a guide what mathematical calculations you need to make. So I drew this picture here on the left, and I put bananas on the vertical axis, apples on the horizontal axis. I can see that if I have 30 bananas and 10 apples, this is going to be a relatively steep slope. If I apply the theorem directly to this problem at hand, the slope of the indifference curve, which is the derivative of bananas with respect to apples, is equal to minus the partial of utility with respect to apples divided by the partial of utility with respect to bananas. So in the next line down, I substitute in the utility function. Charlie's utility function was AB. So if I take the partial of AB with respect to A, that says how does Charlie's utility function change if I give him another apple holding bananas constant? So remember, that's like taking the derivative of 10A with respect to A. That would be 10. So in like manner, the derivative of AB with respect to A is B. And likewise in the denominator, the partial of AB with respect to B is A. So the closed form solution for the slope of Charlie's indifference curve is going to be minus B over A. I can substitute in the values of bananas and apples that he's currently consuming, and the slope of Charlie's indifference curve is -3. Another person that we're going to see a lot of in the practice quizzes is Ambrose. And Ambrose consumes nuts and berries and has a quasilinear utility function. So Ambrose is nonlinear in nuts and he is linear in berries. We're told that he initially consumes 25 nuts and 21 berries. Then what is the largest number of berries he would be willing to give up in return for an additional 11 units of nuts? So again, I recommend drawing the picture. So what I have then is Ambrose started out initially with 25 nuts and 21 berries. And the question asked us that if Ambrose got an additional 11 nuts, so that causes him to go from 25 nuts to 36 nuts, how many berries would he be willing to give up to move along the indifference curve? So after I see this picture, I realize what I need to do is first figure out what is Ambrose's utility level on this indifference curve. So with 25 nuts and 21 berries, I apply that at the top of the column on the right and see that Ambrose's utility level is 41. Right? So 4 times root 25 plus 21 is 41. And then Ambrose, so I need to find out how many berries he would consume to remain on that indifference curve if he had 36 nuts. So 36 nuts give him a utility level of, let's see, 4 times root 36, which is 6. So 4 times 6 is 24. So Ambrose gets a utility of 24 from his 36 nuts. In order to get a total utility level of 41, Ambrose needs 17 berries, right? Because 41 minus 24 is 17. So 17 berries and 36 nuts would keep him on the same indifference curve. So in return for these additional 11 nuts, which take Ambrose from 25 to 36, he would be willing to go from a consumption of 21 berries down to 17 berries. So he would be willing to give up 4 berries for the additional 11 nuts.